Hello, hello, hello. In this episode of What's the Big Idea, we're going to be talking about Newton looks at the moon and the character of physical law. And in my opinion, this is probably the biggest idea of all the biggest ideas that we're going to encounter in Physics 107. I want to Physics 107 is the topic is often referred to as Newtonian physics. You have an entire uh, discipline almost named after a single person. And I'd like to give you the big idea today about what it was that Isaac Newton really achieved. So, up until now, our discussion has been in the realm of what I would call kinematics. And kinematics, as we've said, is all about describing motion, just developing a language to describe in quantitative terms how things are moving. And now we're going to begin delving into a new area, the area of dynamics. And dynamics is really about answering the question of why things move the way they do. And we're going to answer the why in terms of new physical laws. And that is what Isaac Newton was responsible for developing. So we see here a picture of Isaac Newton. This is perhaps a partially apocryphal story of Newton sitting under the apple tree. The part of the story that's true is that in the year 1665, there was a plague in London and surrounding areas. Uh, Isaac Newton was had just finished up his undergraduate work uh, at Cambridge, University of Cambridge, but he was still working there. And because of the pandemic, they shut down Cambridge and they sent all the students home. And Newton was from a family that had a manor in the countryside, about 60 miles um, away from Cambridge, rather pastoral setting. And it is true that Newton in 1665, as a 22-year-old or so, spent an extended period of time on the family estate thinking about physics and thinking perhaps about falling apples. But there's another important part of this image here, and that's the picture of the moon in the background. And it's the connection between the falling apple and the orbiting moon that really was what drew Newton's attention. And there's a famous quote of Isaac Newton's, which is printed on this week's problem set. And it goes something like this: if I have seen further than others, if perhaps I have seen further than others, it is because I have stood on the shoulders of giants. And it really is true. Newton did not work in a vacuum. There were some great thinkers before him whose work Newton was thinking about as he sat in the pasture looking at the apple and the moon. For example, and as you already know, Galileo preceded Newton, and Galileo observed that if you neglect air resistance, that all objects fall uh, towards the center of the Earth at with the same acceleration, an acceleration of 9.8 meters per second squared, independent of their mass. And it doesn't matter whether the object is just dropped from rest or whether it's been thrown in projectile motion. If you're near the Earth's surface, Galileo and others knew that the effect of gravity on the object would be to make it accelerate at g towards the center of the Earth. Well, what about the moon? What was known about the moon? By the time Newton was thinking about this problem, uh, the moon, it was known, orbited the Earth in a roughly circular orbit. And the distance between the Earth and the moon was known pretty well. The distance from the Earth to the moon is 3.85 times 10 to the eighth meters. And it was also known in Newton's time that the radius of the Earth was about 6.4 times 10 to the sixth meters. So those were all known facts. And thus it was easy to calculate the acceleration of the orbiting moon. That was a simple calculation. That's just v squared over REM. And because the period of the moon was known, the moon orbits the Earth about once every 28 days, and therefore the circumference, and because the distance from the Earth to the moon was known, the circumference of the orbit was known. So the speed of the moon's orbit was known. It's about just over 1,000 meters per second. And R sub EM, we just said, is 3.85 times 10 to the eighth meters. And if you plug in the numbers here, I think you'll find that the acceleration of the moon is about 2.73 times 10 to the minus 3 meters per second squared. And of course, that acceleration is directed right towards the center of the circle. In other words, right towards the center of the Earth. So that's a similarity. The falling apple is accelerating towards the center of the Earth, and the orbiting moon is also accelerating towards the center of the Earth. But Newton, of course, noticed that this number, this acceleration of the moon, was much smaller. 2.3 times, 2.73 times 10 to the minus 3 is a much smaller acceleration than the acceleration of the falling apple. In fact, if you calculate the ratio here, the acceleration of the moon is a factor of about 2.79 times 10 to the minus 4 smaller than the acceleration of the falling apple. Okay, and now let me mention just a trio of other giants upon whom shoulders Newton was standing. These are folks by the names of Copernicus, familiar name probably to most of you, a less familiar name, but another important one is the name of Tycho Brahe, and finally the name of Kepler. So these are all scientists who preceded Newton, and what they had noticed sort of collectively over time, Copernicus figured out that the Earth was not the center of the universe, that the Earth and the other planets orbited the sun, and Tycho Brahe was a astronomer, an aristocrat who owned his own observatory, and he made very careful observations of the planet's motions. He recorded them, and this is really an important part of the story. The precision of his measurements ends up being really important in helping Kepler try to make sense of it all. And Kepler notices, sort of systematizes Tycho Brahe's observations into a set of three laws known as Kepler's laws. And we'll talk about Kepler's laws in a week or two. But for now, let me just tell you the main conclusion is that the orbits of the planets around the sun are all elliptically shaped, with the sun at one of the foci of the ellipses. But the acceleration of the planets are always proportional to 1 over the distance to the sun squared. As the planets go around the sun, the farther away they are, the less their acceleration is, but they're always accelerating towards the sun as they orbit the sun. But the magnitude of that acceleration is less the farther away the planet. And this so-called inverse square relationship of how the acceleration depends on the distance was certainly on Newton's mind when he decided to compute the following ratio. He's thinking about the moon going around the Earth, and he just decides to calculate the ratio of the radius of the Earth to the distance, the ratio of that distance to the Earth-Moon distance and to square that number. So the number that he's calculating is 6.4 times 10 to the 6 meters, that's the Earth radius, divided by the Earth-Moon distance, 3.85 times 10 to the 8th meters, and squaring that. And if you do that, the number you get is 2.76 times 10 to the minus 4. And the thing that must have gotten Newton very excited was when he looked at this number and compared it to this number here. So there seems that's those are close enough that it's hard to believe that it's a coincidence, that there's some connection between the acceleration of the moon, the acceleration of the apple, and how they relate to one another, and the radius of the Earth and the Earth-Moon distance. When you take that ratio and square it, you get the same number. So what is going on here? Well, this is where Newton makes his giant leap. So the giant leap that Newton makes is really in the form of developing new fundamental physical laws. And by physical laws, when we call something a law in physics, and particularly if it's a fundamental law, we mean something that can predict a wide range of physical phenomena. So Newton is proposing new physical laws to explain what is going on here. And three of these laws are known collectively as Newton's laws of motion. And we're going to spend a good portion of the rest of the term talking about these laws of motion. But for now, we want to focus on the second of these three laws, Newton's second law of motion, which introduces the idea of forces being responsible for things accelerating. So there's going to be this notion of force acting on objects, and if you know the force that acts on the object and the mass of that object, that's going to enable you to calculate the acceleration of the object. And, one great leap that's part of this vision is that this law, as we said, is universally applicable. So Newton is thinking that it doesn't matter whether it's an apple on Earth or a planet or the moon, all I have to know to calculate the acceleration of an object is to know the mass of that object and the force that's acting on that object. And then the second important, hugely important contribution that Newton makes as he's sitting and thinking about the falling apple and the orbiting moon is to develop his law of universal gravitation, which states that any masses, any two objects that have mass, undergo a mutual attraction to one another. And this is a formula which gives you the strength of that attraction, the strength of the gravitational force that exists between the two masses. And we see that according to this law of universal gravitation, the strength of the force is proportional to 1 over the distance between the masses squared. And the real power of these laws is that taken together, and we will play this out in more detail in the coming week or two, but you can already it's already seems plausible if you look at these laws that taken together, they make a prediction. They predict that so this is an important word to add here. The word is that these laws taken together predict that the acceleration of the moon should be related to the acceleration of the falling apple by this ratio of the radius of the Earth divided by the distance from the Earth to the moon squared. That's the relative factor between the acceleration of the orbiting moon and the acceleration of the falling apple. So this really was a giant leap because prior to Newton developing these ideas, it wasn't at all obvious that the things that were happening on Earth, like apples falling, had anything to do what was going on in the heavens. And Newton is proposing a single theoretical framework, a set of physical laws that can explain a wide range of physical phenomena in the universe, both terrestrial and celestial. That is, Newton is really unifying a unification of terrestrial things on Earth and celestial things in the heaven mechanics. So those are very big ideas indeed. So that's it for this episode of What's the Big Idea? Hope to see you again soon. Bye bye.